Hello, my name is SarahGunnell, and I'm going to give you a brief review of the paper, Quantitative Assessment of Climate and Human Impacts on Surface Water Resources in a Typical Semi-Arid Watershed in the Middle Reaches of the Yellow River from 1985 to 2006. First off, let me tell you about the Yellow River and the study region. The Yellow River is the second largest river in China, and therefore is considered a major water resource for hundreds of millions of people in northwest China. The Middle Reaches stretches from Hakko in Inner Mongolia to Zhengzhou and is approximately 1,206 kilometers long. The study region was the Huangfu River Basin in southern Inner Mongolia. This figure indicates the location of the study area against China and the Yellow River, and these figures show you the location of the Huangfu River Basin in yellow, as well as the rainfall and discharge gauges in the 3,186 km square catchment area. This basin is in a semi-arid climate with 76% of the precipitation falling between June and September, and 53% falling in July and August, making the annual precipitation uneven throughout the year, and as such, runoff is also uneven. Thus, this is a seasonal river with a high peak in discharge and a flood duration. Due to climate fluctuation and human activities, the Middle Reaches have in the past experienced some drier years causing surface water scarcity. The goals of this paper were to determine the quantitative assessment of climate and human impacts on surface water resources, as well as to determine if the simulation utilized could be used for other basins in order to plan and manage water resources for the future. The precipitation data for the models were either recorded at rain gauges or determined from daily precipitation observations. Daily discharge data was collected from 2 gauges in the watershed. The atmospheric, geographical, and human impact information were extracted from online resources. In order to determine the climate and anthropogenic impacts on the river quantitatively, the authors used a few different methodologies. They first utilized a non-parametric test called the Mann-Kendall trend to see if there were any hydrometeorological trends that were increasing or decreasing. To do this, they used the z-test and determined if the null hypothesis was accepted or not. Then they used other test statistics UF sub I to determine if there were any change points in the hydrometeorological data. Next, the authors determined the contribution of climate impacts on the surface water resources. To do this, they used a hydrological model to simulate natural stream flow. Using meteorological data, it was given for the time period. The authors used a model called the Water and Energy Budget Based Distributed Hydrological Model, or WebDHM. This model is able to describe water, energy, and CO2 fluxes in the basin. The land surface temperature was also estimated by the WebDHM. For more information on how this model works, I encourage you to read it under methodologies in the paper. Ultimately, the streamflow change was due to the combined influence of climate and human activities. As this equation indicates, the authors then calculated the individual percentages to determine how much the climate and human activities respectively impacted the streamflow of the river. The Mann-Kendall test ultimately determined that the observed streamflow and mean temperature for the time period were statistically significant, whereas the observed precipitation was not. The observed precipitation increased during the months of March, April, May, and December, January, February, but decreased the other months. On the other hand, mean temperature consistently increased and streamflow consistently decreased every month of the year from 1985 to 2006. The statistical analyses also determined that there was an observed change point for the year of 1998. This indicated that there was a new trend line, or a period that was impacted by climate and human activities, from 1999 to 2006, where stream discharge dramatically decreased. The WebDHM model demonstrated that it could simulate daily and monthly streamflow with good accuracy for the Huangfu River Basin, and therefore the model was applied to simulate natural streamflow during the impacted period of 1999 to 2006. This is shown in these graphs, where red indicated the simulated daily discharge and the black is the observed discharge at the 2 gauge stations from 1985 to 1990, and again from 1991 to 1998. As you can see, there seems to be a good agreement between the model and observed readings. This next figure depicts observed and simulated streamflow for the entire period. It was speculated that some of the differences between simulated and observed values could be from the human impacts on the streamflow. However, the model could only show the hydrological impacts. The observed MODIS and simulated Webb DHM land surface temperatures were also in good agreement, allowing the authors to conclude that the simulation was good in representing both the energy and the water cycles in the basin. The temperature through every season increased and the precipitation decreased, and therefore the evapotranspiration also decreased, resulting in less runoff for the seasonal river. These climate fluctuations were the main players in the reduction of stream discharge. The authors concluded that the human-induced changes that contributed to the decreased streamflow over the impacted period included soil and water conservation projects, artificial water intake, and dam and reservoir construction. In this table, you can see the total land coverage and use has changed since 1998 to 2006. There are more terraced areas, dammed lands, irrigated land, forest land, grassland, and hillsides closed for erosion control. This is important because different types of vegetation will affect soil and land cover conditions. More forest and grasslands also mean that less water makes it down to run off into the streams, and instead the precipitation is caught in the forest canopy to be transpirated. The terraced land would also decrease the amount of runoff, making its way into the stream, and instead increase soil water infiltration. In the watershed, human population and economic growth has increased substantially, causing more water use. For example, from 1998 to 2006, the total water consumption increased by 17.6 meters cubed. The increase in domestic and agricultural water use has created a lot of water stress, especially since it is in conjunction with the decrease in precipitation and increase in the temperature. In addition to this increase of water use, 186 large dams, 211 medium-sized dams, and 259 small dams were built by the end of 2010. They have a storage capacity of nearly 367 million meters cubed, which is larger than the total amount of water resources for the basin. Though they were built to retain floods, the dams also have led to the reduction of downstream runoff. 18 small reservoirs were also recently created for water conservancy. The authors believe that the impact of dams and reservoirs on streamflow should not be ignored when considering the future water resources for the Huangfu-Shuang River Basin. Their research concluded that the observed mean annual streamflow was 34.05 millimeters per year in 1985 to 1998, but only 13.72 millimeters per year in 1999 to 2006, which is 40% of the baseline value. The streamflow was reduced by 10.38 millimeters per year as a result of climate fluctuations, which was estimated to be responsible for 51.03% of the total decrease. In addition, the human-induced decrease in the streamflow was 9.96 millimeters per year, which accounted for 48.97% of the total reduction. Therefore, the human-induced and the climate impacts of the streamflow were relatively the same. In summary, the decrease in discharge was caused by climate fluctuations such as the decrease in precipitation and an increase in the temperature, as well as human impacts such as changes in the land use and cover and creation of dams and reservoirs for water conservancy. The authors were able to use the simulation model as well as the field data in order to prove that the model can be applied to a river basin such as the Huangfu-Shuang. I currently teach violin and stay home with my young children, so unfortunately I don't have much hands-on experience or work experience to go along with this paper, other than the few stream gauges that I utilized in my undergrad. However, I am very fond of my water recreation, such as the kayaking and swimming and fishing. And streamflow in the river is important for all water recreation. I remember growing up in Michigan, and there were a few years in which the creek, which was typically full, ran dry, and the river, which typically flooded every year, had a huge decrease in discharge. I remember that this impacted the local recreational businesses as well as the agriculture that depended on the river. So though I do not have job or much hands-on experience at this time, I can relate to the decrease in stream discharge affecting recreation and local businesses. Also, population and economies are growing rather quickly all around the world and creating more water stress as water consumption increases and climate change continues. The model and mathematical procedures used by the authors in this paper could be applied to other river basins to determine where and why water stress is occurring, and therefore help create solutions for the future. Thank you for listening.
Okay, Nathan, do you like to play in the water?
Yes.
What things do you like to do in the water?
Swim.
Swim, what else?
Swim. Go ice skating.
Ice skating, and anything else?
Go swimming.
Swimming.
And
Do you like to fish?
yes.
Peter, do you like to fish?
If was no water, we couldn't go on boat or fish or swim.
Yeah, is it important that we be able to know what happens to our water so that we can enjoy swimming and boating? Is it important that we learn what happens to our water? Yeah.
And swim.
And swim.
Let's play with water.
Do you want to play with water now? Okay.
And me too.
And you too. Okay.